Beethoven, Mozart and Tchaikovsky. What do these three have in common? That's right, they're all superconductors. But we're not going to be talking about those nobodies today. We're going to be talking about the physical phenomenon that is superconductors and the Meissner effect. Actually they were composers, not conductors. How about you compose some
Let me get to spitting, cause I'll hit you with physics. Cause these equations are amazing, stay alert and look busy. You better sharpen up your shape and get ready to learn, so we can teach you all the physics from your classroom to CERN. Alright, stop.
Today, superconductors. You might remember from GCSE science that if you run a current through a wire, the material that the wire is made out of will have some form of electrical resistance opposing the flow of current. And this is usually a bad thing because it causes some energy to be lost in the form of heat. That's why if you run a lot of current through a very small, thin wire, it sometimes goes red hot, leading to the well-known physics law that at least one student per year will injure themselves in an electricity practical. There's always one. Now, a superconductor is a material that has no electrical resistance when it's cooled to a low enough temperature. Now, when I say it's got no electrical resistance, I don't mean it's got a very little bit. I'm talking zero. I'm talking nil. Zilch, in fact. It has zero electrical resistance. And that's amazing because it means no energy is lost as heat when we pump a lot of current through these materials. Mercury is a really good example. When you cool it to 4.2 Kelvin or negative 269 degrees Celsius, it becomes superconducting. At any temperature above that point, it will have electrical resistance. And when it hits that point below which it becomes superconducting, the critical temperature, it's like going from the M25 at 8 AM on a Tuesday morning to a rural Scottish lane at 3 in the morning. Resistance drops. That metaphor's a bit weird, I know, but we're going to go with it. A lot of the time, a superconductor's critical temperature will be incredibly low. Mercury's, for example, was negative 269 degrees Celsius. To put that into context, that's 3 times colder than the coldest temperature ever recorded on planet Earth, negative 89 degrees Celsius in the Antarctic. And negative 269 degrees Celsius is roughly the same temperature as the water in your shower when you put your foot in too early. That's a very relatable joke right there. Superconductors give rise to another physical phenomenon, the Meissner Effect. Normally, if you place a material, like this one, in a magnetic field, the magnetic field will just go straight through it. And visually, we can represent this magnetic field by using field lines. However, if you now cool this material such that it becomes superconducting, the magnetic field will be spontaneously excluded from the bulk of the material. That's a fancy way of saying the magnetic field will no longer go through the material. Instead, it will take an alternative path around the outside. And this, everybody, is what we call the Meissner Effect, discovered in 1933 and named after Meissner and Ochsenfeld. Now, it's worth saying that if the field now can't go through the material, it can't just disappear. Conservation laws won't let that happen. And this leads to areas around the surface of the material that have a stronger field. And you can tell the field's getting stronger by the bunching of lines in our diagram. See the lines getting closer together? That means the field is stronger there. Now, this effect might manifest itself as, for example, magnetic levitation. If you were to place a magnet on top of this superconducting material, the magnetic field will have no choice of where to go, except push against it and cause it to levitate. And this is how maglev trains work. Except instead of a magnet, you now just whack a train carriage on top of it. Simple enough. Another place you might see superconductors is if you had 2 competitor mining companies. Each company is run by its own greedy old boss who only really cares about money. Both bosses realise that they're wasting a lot of energy to power the minecarts to go back and forth, and as such it's costing them a lot of money. However, one of the bosses, the smarter one, realises that he could use superconductors and the Meissner effect. Using magnetic levitation, he can make frictionless minecart rails. So you could say that the wiser miner miser hires a Meissner finder to source superconducting materials. The reason behind superconductivity and the Meissner effect is based in quantum mechanics, which means that these are an example of a macroscopic or large-scale quantum effect. It's also worth mentioning that there are two types of superconductors, type 1 and type 2, inventively named. And in type 1 superconductors, the Meissner effect occurs in pretty much the same way, however for type 2 it can get a little bit more hairy. Also, do you remember that bit in the video earlier where I said that the magnetic field is excluded from the material? Yeah, that's not entirely true. In reality, the magnetic field can penetrate into the material a little bit, and that's called the London penetration depth, and it usually has a value between 50 and 500 nanometers. And that's roughly equivalent to my height.
The joke here is I'm short.
And that's an introduction to superconductivity and the Meissner effect. If you found the video helpful or at least interesting, make sure you drop a like and maybe even consider subscribing to the channel to see more content like this. The comments box is always open, so if you have a question or you'd just like to start a discussion, by all means drop a comment down below. And I'll see you in the next introductory video. Catch you later.